We're going to continue our discussion of methods of using the derivative to understand properties of the shape of our original graph. But now we're going to extend the idea to what's called the second derivative, which is the derivative of the derivative. So one way to think about this is to remember one of the models for the derivative is that the derivative measures slope. So the derivative of the derivative measures the rate of change of the slope. So in other words, if you looked at a graph and sort of imagined yourself looking left to right across the graph, you could ask yourself, how are the slopes changing? What's the rate of change of the slopes? So for example, if we have a graph like this one that's from problem 8 from the 12.2 homework, if I wanted to measure slope at a few places, I could imagine, sort of my tangent line. So the slope here, for example, looks to be about negative 2. So this line is going over 1 down 2, more or less. So the slope's about negative 2. Then when we get here, the slope is 0. When we get over here, the slope is sort of more close to positive 2. So what we see is if we look left to right, that as we go from here to here to here, the slopes are increasing. So the slope was negative, then 0, then positive. So the slopes are going up. In terms of the geometry of the graph, slopes increasing cause the graph to have a cup upward shape. So we call that concave up. Concave up means that the graph has an upward cup shape, as if it could hold water. Conversely, if the slopes are decreasing, so for example here the slope here is about positive 2, then 0, then negative. So across here the slopes are decreasing, and that gives the graph a downward cup shape. So this would be called concave down. So we can tell from whether the slopes are increasing or decreasing, we can tell whether the graph's going to have this cup up or cup down shape. And so that's what we mean when we say we measure concavity. The concavity just refers to the cup shape of the graph. So if I wanted to imagine a sign chart here, so if I gave myself a number line across the top here, I'll put it down here. So if I had a number line here and I wanted to mark on the number line whether I had an upward cup shape or a downward cup shape, then my divisions are going to be here. So right around here is a point where the graph stops being concave up and starts being concave down. That changes again when I get to this point. The graph is concave down to here, but right at this point it starts to be cupped upward. Notice that it doesn't have to really complete the cup to say that it's a concave up shape. Just the fact that it looks like it's part of an upward cup is enough to say that it's concave up. So we put another divider here and say our graph is concave up through this region. When we get to this point, the graph starts being cupped downward again until it gets to this point. So all the way to here, we have a downward cup shape. And then from here on, we have an upward cup shape. So those are properties of the shape of my f. The way we measure that is with the second derivative. And we'll talk about computing the second derivative in a minute. But the correspondence between concavity and second derivative is simply that a positive second derivative means we have an upward cup shape. A negative second derivative means downward, and so on. And so if I drew a sign chart for the second derivative for this particular graph, it would look like this. It would be positive, then negative, then positive, then negative, then positive again. And so what I'll be doing is creating the sign chart for the second derivative, and then from that we'll be able to recreate the geometry of the curve and analyzing the shape of the curve. For this particular problem, they give us the sign chart and ask us to locate which of the graphs look like that. I just picked one of these randomly. I think I picked the first one. But you can see that the sign chart here does not match the sign chart that I just drew. So I didn't do this problem, didn't do number 8 for you here, but I can tell you that this one is not it. That's not the right choice. So let's go on and talk about how to compute the second derivative. I said it's the derivative of the derivative, which is exactly what it is. So it's actually very easy to compute. All we have to do is to find the second derivative, we need to first find the first derivative formula. So here's my function. So I'll have 5 times the derivative of x to the 4th is 4x cubed. The derivative of x squared is 2x. So this guy. The derivative of 3x is 3, and the derivative of the minus 6 part, of course, is 0. Now, I do need to take the derivative of that answer, and so it's worthwhile to me to at least simplify this superficially, even if it's just the really quick things like multiply 5 times 4 together and multiply 7 times 2 together, because the simpler this is, the easier my next derivative step will be. So once I have the formula for the first derivative, I simply take the second derivative by taking the derivative of that answer. And we've seen some pretty complicated looking first derivatives, so you can imagine that the second derivative is not always easy to calculate, but it's not going to require any new rules. There's nothing that we've calculated from the first derivative that gave us something that we did not know the rule for doing the derivative again. So in this case, I'll have 60x squared minus 14 as my answer. Here's one that has a more complicated first derivative. I just wanted to do an example of this so you could kind of see what comes up and see that simplifying your first derivative answer is really the key to being able to do the second derivative easily. So in this case, my first derivative is going to use the quotient rule. The quotient rule says that I should have the denominator times the derivative of the numerator minus the other way around. So numerator times derivative of the denominator. And of course, that's all divided by the denominator squared. So not only do I need to do this derivative by finishing what I've written here, so the derivative of log x, remember, is 1 over x, and the derivative of x to the 10th is 10x to the 9th. But it's in my interest to simplify this as much as possible before continuing. So for example, this x to the 10th squared, that's going to get complicated in a minute if I don't go ahead and write that as x to the 20th power. But I can do more than that. I can simplify my numerator, x to the 10th times 1 over x, is just x to the 9th. Essentially, this is 10x's multiplied together, and you're dividing by 1x, so you're canceling out one of these 10x's with that x in the denominator. And then here I have 10 times x to the 9th. I'm just going to rearrange that a little bit so I can see the common factor. And you can see that there's an x to the 9th term in both places there. So I can factor out x to the 9th. And then finally I can simplify this a little bit because I have 9x's here and 20x's here. So I can cancel 9 of those x's and have just x to the 11th. So my first derivative, I'm not done yet, but my first derivative is 1 minus 10 log x over x to the 11th. If I had not simplified that, I would have to be working with this awful thing up here to calculate my second derivative. So working with this directly and taking the derivative of that would be very difficult. And so, so doing this extra simplification, even though before we didn't bother, wasn't really necessary, now it's definitely worthwhile to do it. So my second derivative is just going to be the derivative of this answer that I got. And again, I just used the quotient rule, so I won't do this one all the way to the end. I'm running out of room here, but I'm just going to repeat exactly the same process. Denominator times derivative of the numerator minus the other way around. Divided by the denominator squared. And when you resolve these couple of derivatives, you will be able to do a little bit of simplification like we did before, but there won't be a a great reason to simplify it all the way to the end like we did here, because as soon as that's the final answer, we really don't have anything else we're being told to do with it.